welcome back. We've got a couple announcements. We've got some new stuff up on the blog. One sec, I'm going to play with the lights a bit. Is that? Oh, that's not helping. Okay, sweet. Yeah, ooh, now it's very romantic. Okay, great. So there's a couple things on the blog I want to point out. So homework 5 is it's now available. Okay, so this is assigned today and due next week. For people who are not sure if they want to stay in the course, for people who they're not totally certain about their marks, the drop deadline is next Monday. Okay, so the time to make that choice is this week. Consider whether you want to stay in the course or drop. I will not be offended at all if you drop. It's okay. You want to keep your high average and stuff. So that's good. So homework 5, as I was saying, it's up here. Okay. There's some textbook questions. Some stuff about material from today's lecture. Okay, so that's available online. One slight change to the syllabus. Some people pointed out to me that there was a timing issue in the syllabus that couldn't be resolved. So homework 6 is going to be assigned in week 11 instead of week 12. Okay, so homework 6 will come out next week. So I'll just show you where that occurs in the syllabus. So in week 11, homework 6 will come out. So in the old version of the syllabus, the homework was here. Sorry, it was here, and then I realized there'd be no time to hand it back to you. If it's assigned in the last week, then you never get it back before the exam. So it will be here instead. Okay, so you'll get it that week. Okay, very good. So that's a slight change. Okay, but that's in the future. Okay. It's like I want to see if these will crash the computer. How badly will they crash our computer? Okay, sweet. Not so bad. Okay, let's let that one load. Wow. Okay, sweet. All right, so we'll get to those guys in a little bit. Very good. Board right. Yeah, so I want the boards off. Okay, good. Okay, so this week we are going to get into integration, which is a topic that we haven't talked about so far. So we're going to switch gears a little bit. And we're going to jump right to 5.2. So we covered some material in chapter 4. There's not going to be any more material from chapter 4. We're going to jump right to chapter 5 now. Okay, so I just want to recall how we calculate areas in our first year calculus course. So that this guy, this integral, right, when we write this formula, it calculates an area for us. So it calculates what is called the signed area of the function over that interval. Okay, so I say signed area because if the function goes below the x-axis, the area becomes negative. And usually we don't think of area as being a negative quantity. But this time it can have a sign associated with it. Okay, and our key formula concerning these definite integrals is the so-called fundamental theorem of calculus. Okay, the fundamental theorem of calculus tells us that we can write that signed area as a difference of two things, where this big f function has as its derivative the little f function. Okay, so this is what we call an antiderivative of little f. Okay, so this is our sort of a statement we're going to be coming back to over and over again today. I just want to show how this calculates an area for us with a simple example. Okay, so let's find the area bounded by these two curves. Right, standard exercise. Okay, so what do we do here? We draw in the curves. Right, the region bounded by these two curves is this guy in the middle. All right, and we're looking for the area of the shaded region. So the area, before we go on, we should find these points of intersection here. Right, so we solve where these two curves intersect. We get 1, 0, negative 1, 0. So our area will be the integral of something that I'll call the length at x. Okay, what's length measuring? Length is measuring the length of these vertical segments. Okay, so we can get the area as an integral of lengths. Okay, so the length of that vertical segment is 1 minus x to 0. Yeah, so it'll be 1 minus x down to 0. So it'll be 1 minus x squared. Okay. Now we take an antiderivative of this guy. So we find a function whose derivative is 1. Yeah? That'll be x. Then something whose derivative is x squared. That would be a third x cubed. Right? We take the derivative of x cubed. 3 comes down, cancels. We get x squared. Good. Okay, when I write these square brackets with bounds, I'm saying where the integral's happening. So what am I going to plug into the fundamental theorem of calculus to get my result? Okay, so we wind up getting the fundamental theorem of calculus says that we get we plug in our top bound, we plug in 1, we get 1 minus a third 1 cubed. Okay, and then we put in negative 1, and we get this guy. Okay, do a bit of arithmetic. And we get 4/3. Okay, so I just wanted to go through this to set up this notation with the square brackets as meaning that we use the fundamental theorem of calculus. Okay, so using fundamental theorem of calculus, we get this difference here, and it winds up giving us an area of 4/3. Okay, so with that said regarding areas, now I want to move on to how do we do this in multiple dimensions? What's going on in multiple dimensions? Okay, so this is one of the sort of the more beautiful ideas in the course. And it's something called Cavalieri's Principle. Okay, Cavalieri was Galileo's student. Okay, so Galileo, famous mathematician, astronomer. One of his students was Cavalieri. They wound up working together at the University of Bologna. And he came up with the following idea. Okay, the integral of volume is, the integral of area is volume. Okay, that if we do this process with length, but we replace it with area, we're gonna get volumes now. Okay, so this winds up having a very nice consequence. Okay, so if two bodies have the same horizontal slice area functions, then they have the exact same volume. Okay, so if you've got two bodies that have the same area functions when you slice them horizontally, then they wind up having the same volume. So if you look up at the overhead with the blog there, you'll see that there's a stack of coins. And this is meant to sort of illustrate Cavalieri's principle, that as we move the coins from a horizontal stack to some kind of bent stack, they have the same volume no matter how we move them. So here they're as a cylinder, and then there they're sort of as like a leaning Tower of Pisa thing. Galileo would have been proud. These guys have the same volume. So if we arrange them in any which way, they have the same horizontal slices. All the slices are equally large. So they'll have the same volume. Okay? A better sort of demo of that, that's much bigger, I found online, and I think this is super cool. So here we've got two collections of slabs, and we can move them over from this kind of complicated S shape here. We can move them one by one and fill them in to this prism shape. Okay, so they have the same volume, the prism and this weird S-shape thing. And you can deform the stack if you want. Right, so no matter how you deform the stack, they'll have the same volume. Okay, so that's Cavalieri's principle. Are there questions or thoughts there? Yes? That's the idea. So actually putting hypotheses that make this 100% rigorous is hard. But yes, this is true for limitingly thin slices, infinitesimally thin slices. Okay, so I want to say a little bit about Cavalieri's principle. Okay, so let's draw 3 cones, and we'll make sure they all have the same volume. Okay, so if we've got a cone of height h and radius r, and there's a right angle here, then we can shift all the slabs slightly. Okay, and now we'll get height h here, and radius r here. Or if we shift them we can shift them in the other direction and get the same volume, because all of the cross-sectional areas of these guys right, these orange regions will have the same areas. Okay, so let's use this idea to calculate a volume that we already know to make sure that it works in practice. Okay, so let's find the volume of a rectangular prism. Okay, so what does that look like? What's a rectangular prism? Okay, we're going to have some box. That's a rectangle on each side. Okay, we'll have our height here, base here, and width here. All right, so we know that the volume ought to be height times base times width, yeah? So we've got that. Now let's try and get it from this notion that the integral of area is volume. Okay, so we're going to set up an integral. So we want our volume to be the integral just like we did with length, now we're going to do with area. So we integrate area, and let's follow our usual convention here, calling this the x-axis, this the y-axis, and this the z-axis. So the thing that we want to integrate is the area at a particular value of x. Okay, so we're going to go from 0 to w. And we need to know the cross-sectional area at that cross-section. Okay, so we're looking for the area of those slices. The area at x. Okay, so if we cut this thing along a particular value of x, we should get a rectangle of size base times width, right? Going, is that right? Base times height, thank you. Yeah, we go across the base from left to right, and then height up and down. Okay, now this is the kind of thing that we can integrate. So we need something whose derivative is base times height. We notice that there's no x's in here, so it's a constant. So we say base times height times x from 0 to w. Okay, so we get the formula we were expecting for that cross-sectional area. Okay. Right, so I want to write this down just to highlight the sort of the idea of the setup. How do we set these kinds of things up? Okay. Okay, another application of Cavalieri is very, very nice. This argument, I think, is originally due to Archimedes. Okay, so he came up with it in like 200 BC or something. Okay, so here's what we do. So claim Okay, so the claim is as follows. Okay, so lots of words there. The volume of a hemisphere of radius r and a cone of radius r and height r equals the volume of a cylinder of height and radius r. Okay, so there's a great deal of words there. The idea is that these two volumes added together equal this guy. Okay, so I want to get this from Cavalieri's principle. Okay, so our first step is going to be setting up some equations for these guys. Okay, that's the equation for the hemisphere, right? But we only care about z positive. The cone is this guy. Okay, notice that if we go up to height r, then we get a circle of radius r. Yeah, if we go up to height r on the cone, we get a circle of radius r. Okay, so what we need to do is we need to find the cross-sectional areas. Okay. So first off, we have to find what the cross sections look like. So are things okay? Questions or thoughts? Yeah, is everything okay? Yeah, good? Okay. Okay. Sorry, I couldn't quite hear the comment. Okay. All right. All right. So at this height, what happens? We get the following thing. Okay. So let's figure out what that region is in the plane. So this is, on the sphere, we get a circle of radius r squared minus k squared. Okay, now let's see what happens with the next guy, with the cone. We get this. Okay. All right, so at that particular height, we get a circle of radius k. Okay, so what's that saying? if we take a cut at z is equal to k here, and z is equal to k here, then the cross sections are two circles. Like this, yeah? And we know the areas of those circles. We get the following thing. So adding the two areas together, we get pi k squared plus pi r squared minus k squared all squared. Okay, and now here I think is probably the nicest cancellation ever made. It's crazy. I mean, this argument was first written down 22 centuries ago, and it's still really beautiful. So these guys cancel, and we get pi r squared. Okay, so when we add up these two red regions, we get that region there. Okay, so this guy here is a circle of radius r. Right, so these two slices add up to be this slice. Okay, so taking the integral over this, we get the volume we're looking for. Okay, so someone did a computer animation of this. So this is Archimedes' proof for the volume of a sphere, the volume of a cone. Check it out. So as we move that z equals k value, it cuts at a different plane. So that sort of rising water level there, that green thing, is the plane that we're cutting at. That's in our proof that z is equal to k. Okay, and then the outside region here, the orange the orange sort of donut shape is the remainder. So as the disk rises up, the annulus always has the same area. Ooh. Ah. It's so satisfying. Before coming to lecture, I did this for like 10 minutes. I was, ooh. Ah. It's so good. Okay, so there's a very classical application of Cavalieri's method, or Cavalieri's idea. So Archimedes liked this so much, this argument so much, that he wanted it on his gravestone. It's like so key. Okay, never mind. Very good. Okay, good. Now we've got lights. Okay, so now let's do sort of a more complicated calculation of a volume using these same ideas. Okay, find the volume under this thing. And above the following region in the plane. Okay, for what it's worth, there's usually an abbreviation that's quite common. If you've got these two intervals, it's often written like this. So you take the x coordinates, which are these guys, and you multiply them by the y coordinates, which are those guys. Okay, so let's find the volume under this surface and above this rectangle. Okay, so we set up an integral. And we say, using Cavalieri's principle, that this should be the integral from -1 to 1 of some area function. Which area function? Well, the area under this thing, right? So what we're going to do is we imagine that we have our region here, and over top of it there's sitting this kind of parabola shape. Okay, so it's sitting over top of the region kind of like a dome. And now what we're going to do is we're going to cut horizontally, just like we did with the box. Okay, so we pick a value of x. We go up over the dome and down. Okay, kind of hard to see what's going on there, but let's set it up just the way that we did in first year calculus, I guess. So we'll say the area of that slice is the region under some curve. So this will be the integral of 2 minus x squared minus y squared dy dx. Okay, so this is measuring the area of that red slice. Okay, very good. So this is exactly the same idea, expressing this as a sum of lengths to calculate an area. Should we go into more detail about how that setup works? Yes?
I have a question about the 1, -1 integral.
Sure.
Which one's the x and which one's the y? Like, how do you know?
Yeah, that's a great question. Do we have time to get into the full details? Okay, so we're going to talk about this more next lecture. The idea is we start off with area x dx, right? So that's our formula for Cavalieri's principle. And then we need to calculate the inside thing there. We need to calculate this area. So we set that up as an integral in y. So what's going on there? Right, to calculate the area of this red slice, we're moving along the y-axis now. And we're adding up those lengths that go that way. Okay, so when we cut the dome, we are adding up some stuff in y, and that's where the dy comes from. We'll get more into the details of that choice next lecture, though. Okay. Very good. So let's use our first year calculus know-how on this. So here we've got a constant. We integrate that as 2. Now, currently we're acting under dy. So for us, x is constant right now. Right. So we integrate this thing, treating x as constant, treating 2 as constant. Y is currently the only variable we care about here. And we get this. So the fundamental theorem of calculus tells us to plug in our bounds. So we plug in our upper bound. Then we subtract off what happens when we plug in our lower bound. Sorry, dx. Okay, and now we, oh, yes. Oh, yes, sorry, z. Sorry, thank you. Yeah, sorry, it's the z coordinate is the one with the dome. Okay. Sweet, good. We get here. Okay, so now we've got 2 minus minus gives us plus. Minus 2x squared. Minus 2/3. Okay, so that would give us 12, so 10/3. Wait, something funny has happened. We integrate in y. We need dx. Okay. Now we've got something that we integrate in x again. And here. Good. Okay, putting in our bounds. Here. Okay. Okay, so what are the steps here? We find a formula for the area of the horizontal, for the area of the slices in x. We integrate in y to find the area of those slices. We put in the resulting fundamental theorem of calculus statement. Do a little bit of arithmetic. Then we've got something that just involves x now. Notice that when we integrate in y, we get a formula that only depends on x. We take that formula that only depends on x, integrate it and get a final number which represents the volume. Okay, so to kind of make an, oh yes, yep. Let's see, should these 2/3 be canceled out? Okay, let's double check. Okay, so writing out all the parts of the equation there, we get, okay, these guys definitely add up to 20/3, that's good. Then we've got minus, oh geez, there's a lot of minuses now. Let's see. Minus, yeah, okay, so minus, okay, yeah, no, I think it's good. Okay, so let's try and make a method out of this. To find the volume under this, okay, so what do we do to find the volume? First, we integrate in x. Right? X is going to run from A to B. Okay, but to find the area at that value of x, we need to do something involving y. So now we'll add up the areas of the slices at x. Like this. Okay, so we first calculate the integral in y, and then we take the integral of that in x. Okay, very good. So I think the question about order of integration, dy dx, dx dy, very interesting. We'll talk about that on Thursday. Oh, if you didn't pick up your remark, I have them here. And if you wrote the deferred midterm, they're also here.